I'm going to talk about Superman. I think there's an overload of information, so we can all wake up and then get there. By the way, I'm not a doctor, I'm a good patient. I can be a good patient or a case study for everyone. Let me just start by introduction. I'm Siddartha Durairajan, CEO and co-founder of LENR. My colleague Agastya, I guess his age is the experience of all of you in LENR. So I guess he was in, I would skip the comment. My other co-founders are the ones who created the Iron Dome in India, which really protected us during the conflict that happened last month. So we are now on the more productive or more environmental conscious side of building LENR. Before I step on to the acceleration on how and where we went on, let me just give you a couple of conversations. Like my previous speakers have a COP of almost 510. We've always tried to navigate between what is reality, what is possible, and how do we commercialize. And that's where our entire conversation went through. So this presentation is going to be more on to how are we going to look at what do we have and how do we commercialize and how do we take this from here to a higher COP with the collaboration of the entire team. I'll now leave it to Agastya to run through the presentation.
Hello everyone, very good morning. So the first slide, these were the results that were presented in the ICCF26, and in this presentation we'll be talking about after the presentation and the formalization of the company LENR, where we are right now and what we are doing. So on the graph on the left that you see is a calorimetry graph for two devices. One is the calibration and active that was shown in ICCF26. Here we were at a COP of 1.3. Right now we are at a COP of 1.78. I'll also be discussing on how we got there and what we are doing here in the labs. We tested our reactors in quadrupole mass spectrometry, and we found out that as you see below in the below image, there are 4 reactors kept, out of which R1, R2, R3 are all R1, R2, R3 are all active devices, and the C is a calibration device. So the gas was evacuated and into the quadrupole mass spectrometer, and it was observed that there was helium-3 and helium-4. As you see, there is a decrease in the concentrations from R3, R2 and R1. The difference between R3, R2 and R1 were that they were ran for different time periods, 1 month, 2 months and 3 months. So this is where we were two years back. Yeah. So this is the basic form factor on the left that you see. We give an input thermal excitation to the device. We use pure hydrogen inside the device. We have also experimented with a lot of other isotopic mixtures as well. But we found out that if you are to commercialize this device, it's better to have hydrogen gas rather than have isotopes of hydrogen inside the device system. There is a slight increase in the performance when you use different hydrogen and a deuterium mixture inside the device. We have developed a proprietary LENR catalyst that is based on nickel and palladium, and the process is patented. On the right side, you see on the first image, these are the various form factors of our devices. So initially we started with a cylindrical device, but we noticed that probably this device may not be able to be used for any engineering application. So we started to tweak the system in terms of engineering methods on how we can extract the heat, how it can be useful for an application. That's how we came to 2 form factors. One is a tubular based ecosystem, which is used for your power generation, heat transfer via convection methods. And another one of it is based on a tile profile, a flat reactor. We have one of it over here. So this was particularly developed keeping the space application in mind. So by talking to the relevant stakeholders, we found that heat is a real problem in space. And right now, the battery capacities that are sized in the satellites, they are sized as per the heating requirements of the satellites. So say per se, in your mission profile, there is a time period where you're not able to generate electricity via the solar panels. Then these batteries take over, and the batteries keep the electronics warm at around 20 degrees Celsius. So this consumes a lot of power, and there have been a lot of failures in the past due to not being able to heat it properly, or the battery not being able to store sufficient charge to keep on expending energy to heat up the electronics. So this is the value proposition. So right now we are at a 1.78 COP. So the flat devices we built is basically to replace the traditional heating devices in a satellite, where the same device will be producing heat. And we are also developing a use case where we able to able to generate electricity out of this device. Now on the right, you see a device with a clamping plate. So this was this was the first prototype to check how these devices work in a space environment. So these were taken to a vacuum test chamber. They were covered with MLI blankets connected to various thermocouples. And since there is no convection and radiation losses, all the heat was taken away through conduction. So this is how we are modeling the system for satellite, and we are testing it on ground. Yeah, coming to the system. So right now we are at a efficiency of 1.78. So we had a talk with Department of Atomic Energy of India as well. So this letter that is shown at the left-hand side, it is in reference to one of our patents which have LENR in it, and because of the word nuclear, it got flagged. And 3 weeks back, we received a letter stating that you do not come under any atomic regulations because you do not use any restricted materials as well as any radioactive materials. So you are free to commercialize, basically. This is what they are trying to say. So coming to the system, we are at an efficiency of 1.78 right now. Our reactors work by hydrogen gas loading. The journey from COP 1.3 to 1.78 was a fascinating one. All these experiments that were conducted from the last 11 years, we ported the data to an ML tool and optimized the certain parameters, and there we significantly improved the performance of the reactor from 1.3 to 1.5, now 1.78. So this is the product line that we are talking about. The company is based on two thought process. One is cogeneration systems for your extraterrestrial applications and cogeneration system for your terrestrial applications. So right now in October, we'll be sending one of our devices to space to get the space heritage for the heating systems, as well as a concept that will be generating electricity. So on the left, you see assembly of the reactor and the mission payload that we'll be sending. So it is a flat LENR reactor, on top of which we have a TEG array to quantify the power generated, as well as to generate electricity. Now the initial mission will be carried out by supplying an external heat source. But the intended application is to take heat away from GPUs, from compute satellites, amplify that, and get a higher energy recovery. So with one launch, we are hitting two birds, I would like to say. One is getting our system space tested and getting the space heritage for a heating system, as well as getting the characteristics of the performance in space, as well as generating electricity for compute satellites by doing a waste heat energy recovery in space. On the right side, you see terrestrial applications that we are developing right now. So the initial thought process is to generate steam for pharmaceutical industries and scale it up to higher grade steam and higher process requirements. We are also integrating an LENR-based heat exchanger to a Stirling device to generate electricity. On the right, this is a concept for a 1 megawatt power generation unit that will be comprised of modules of these reactors. Here's one thing that I'd like to say. Scaling up in the requirements for the energy, you can look at it in two ways. One is scaling down the systems to a very small size. Here you have a good control over your manufacturing process through which you are creating the reactors. And the other one is scaling up. So right now in our company, we are doing both approaches. The space, in the space side of things, we are reducing the volume of the reactors and making it as energy dense as possible. For power generation, we could look into that as well. We are also parallelly developing the bigger tubular elements. Right now, it is in progress. Yeah. So on the right side, you see a system over here. This is basically a test setup for our space device that we'll be sending on October. For this to simulate an environment, we have a Peltier cooler on top of it to have a cold plate, and the rest of it is the assembly as shown on the left. So these are the applications we are getting into right now. Creation of a boiler for steam generation. Initially, it would be a saturated steam generation and would be scaled up systematically. This is an interesting case where we would like to look at energy recovery in the LENR-based heat amplifier that we are trying to build right now. So it takes in the heat away from the stream and would be amplifying through LENR process. The input phase change would be provided by the LENR boiler that will be developed in the previous, that was shown in the previous slide. So the approach towards commercialization is modularizing each equipment systematically and then scaling it up efficiently and doing many things parallelly, so that once we reach a maturity somewhere, we also reach a maturity in the other applications as well. So, yeah.
So as you have noticed that we are keen for commercialization, and as my previous speakers did articulate as well, the concept of LENR has been there for a long time, but I think together what we can do can be much more powerful. So what we are asking with the audience today is collaboration in the space of LENR enhancement. Like I see many faces here whom we have spoken over online or we've connected, but I think the knowledge sharing here is critical. When I say knowledge sharing here, I mean, I don't have to burn fingers where you have already burnt or vice versa. So we could probably literally have each other's back while we go forward in this journey. The second interesting point is one of my previous speakers did talk about our organic Rankine cycle, and we are also keen on a supercritical CO2. And the dream here is to, if you had looked at the device that we have built, I mean, this is my actual reactor that is right now working in my labs in Hyderabad. So if I'm able to cascade this reactor, I'm at a COP of 1.78, but if I'm able to cascade this reactor, this output from here can be an input for the other device and it can go on, which means I can hit a COP of 2030. Yes, but it calls for a lot of thermodynamics. I mean, LENR is just one fundamental here, but it calls a lot of expertise on thermodynamics and other ecosystem. So the second ask is a collaborative approach in trying to see, hey, what is your strength and what is my strength? Let's piggyback on each other's strength. Another interesting point which one of other previous speakers spoke about AI and ML tool is, we did use the power of AI and ML in a big way. Incidentally, the AI tool that they were building was more on a search database. But I'm saying I'm willing to share my experimental database. Let's figure out how we can use the experimental database to see how we can scale up. Just for your understanding, what Agastya just mentioned, our AI and
5 minutes. 5 minutes.
yeah, our AI tool has spit out close to around 16 parameters that are defining my COP, which means right, going from a brute force lab method experiment to I am getting to a predictive model. So we have a prediction of say 10 COP in the next 6 months. We know what are the parameters to change. So I would like to see if all of us could collaborate together to build a singular platform, the one, one source of truth, which can have all these ecosystem built in, so that we could be the owners. I mean, why should hot fusion get all the attention? Let cold fusion also get what it deserves. And the last point that I would definitely like to state here in my ask is safety and certification. I mean, probably we are sorted with India on how our safety and certification is happening, because the Department of Atomic Energy is the de facto governing body and they have okayed it. But I would want to do that globally as well. Now, what I have to offer, I'm an open book. We are there. You can visit our labs. You can look at our space products. I mean, I'm more than happy to work together on commercialization. And investment pool is a very critical thing. We are currently closing our Series A, pre-Series A funding round. And as rightly articulated, with more funds, we can go much further more. So I'm also open for advisory boards, people who are willing to come on board and then work together, more than happy to do that. So together we can move hot to cold. I mean, the entire storyboard can move from hot fusion to cold fusion. And again, I have been in an entrepreneurial journey all my 30 years. I have built companies. I've built the world's first electric tractor, sold it to a different company. So I think I will be able to bring in a very interesting ecosystem that can also bring funding to all of us together. So that is another way. And I like my first presenter in yesterday who coined the word leap. I mean, I don't know if it is a misnomer to call nuclear reaction, but I would like to take that leap forward into future. Thank you.
Thank you, presentations. Any questions?
So I think broadly speaking in this space, it's really important to tame commercial claims and not overstate the case. You know, and it's interesting, Siddartha, you say you're an open book, but we had a conversation right a few months ago, and I asked to see some data that would demonstrate that actually you guys have something anomalous, and you weren't so keen. You know, I visited the labs in Bengaluru a year and a half ago before this sort of commercial enterprise spun up, and people were trying to do good work there. And I suggested some experiments to do to actually demonstrate that there is anything anomalous going on. So for example, you guys show, purportedly have helium-3 and helium-4 detection, but you show no mass spectrometry data, just time series data. You can't make helium-3 and helium-4 claims if you're not even going to show the spectrometry data. One of the things I mentioned to you, right, is that if you have your active material and your control, because you guys are measuring temperature from the surface of the vacuum chambers. And if you have different materials, a control and an active material, which have like a nickel mesh or something like this, if the emissivities are different for different loading, then the thermal radiation will also change. And so that's a prosaic explanation for different surface temperatures. And it's especially interesting that you guys only see the effects at high temperatures, and it goes like T to the fourth. So, but these are the kinds of things that you need to actually do before you sort of go around and claim with, press releases that you have anything anomalous. And so, tame the commercial claims, I think.
I will detest from commenting on any of your claims here, but I would say I'm an open book as long as you're willing to come and partner together, but not critic. And I think everybody in this room understand that there is a lot of unknown variables in a LENR field. And it is not just about, see, anomalies are there. Anomalies is what and the reason why we are here. So I would probably take this offline with you. You want to answer? I can take it offline. we'll take it offline.
Yeah, okay.
Last one person, please.
Yeah, it's more of a comment regarding your ask list. You mentioned like another way or a more efficient way of sharing knowledge. I'm part of a group. Now we are 4 people. We are Van Tasner. We are building on the side some kind of decentralized network for sharing scientific knowledge along the lines of GitHub for anybody who works in code. So we apply the same principle of authorship and decentralized control of evolution of scientific ideas. And we do it outside our commercial operations because we believe that any kind of new technology, deep tech, must be based on fundamental science, physics, chemistry, and knowledge, which is shared and open source. Then there is business, and there is the market, and wins who best serves the market. But so this is an open call for you and for anybody who wants to go outside of the normal gatekeeping of the actual system. Open offer to anybody.
Yeah, I mean, that's a good effort, and incidentally, we thought about a GitHub kind of a concept.
It's in the air. Many people are thinking about this.
Yeah. We did create a notebook-based ecosystem, which is already allowing us to do all those things. But again, it depends on how many are willing to come forward. Yeah, I'm willing to put my first foot forward, but it is with the intent that this is going to be used for scaling our own requirements. It is not about, I mean, that's the intent that needs to be clear. Otherwise, yes.
I mean, we take example from real companies which actually have done this. Arduino, for example, the hardware is open source, but they're getting rich anyway.
Correct.
The Prusa printer, all the schematics is online, but it's a thriving business. So this can be done. It has already been shown to be possible.
And that's how we will be able to go from where we are today to maybe where hot fusion is today. I mean, again, hot fusion guys are there without even having to generate 1 ounce of energy, and we have so much to do, but we are not really cohesive in our effort, you know. We are all looking with each other with an eye of suspicion. So I think we should come out of that boundaries.
Okay. Thank you, your presentations.
Thank you very much.
Close these sessions.